Pile à l'heure.
Ouais. 5h08. Pile.
Incroyable.
Bon.
Magnifique.
Ah, le meeting, c'était comme clair sans l'être, là.
Le meeting de tantôt? Ouais. Oui. Ben, en fait, moi, Marie-Ève a été impliquée là-dedans au bout depuis le début. Fait que j'en entends parler tous les jours, là. C'est quelque chose. C'est quelque chose. Excusez-moi pour mon retard. C'est une journée fatigante. C'est une journée très fatigante. Salut, Anthony Bilodeau.
Bonjour, Daniel Côté.
C'est moi. Bon. Je suis fatigué. Maudit que je suis fatigué. Fait que je vais envoyer un petit message à Shadi et à Tweedledoo. Elaï, tu seras pas là? Excusez-moi. Je pense que ça va être temps que les enfants retournent à l'école.
C'est ça qu'on sent.
C'est épuisant. C'est épuisant. On va à pied.
À comme planter.
Comment? T'as planté?
Ça a bougé lentement. Mais ça va.
Un peu. Là, il faut que je trouve Shadi et Elaï. Un peu. C'est pas long. Julien, Anthony, OK. Voyons, Caltar de patente. Bon, OK. Mathieu Laware. OK. Replay. OK. Bon.
Hello.
Caltar de patente. Hello, Shadi.
Hello, how are you?
I'm all right. Still liking your apartment?
Yes, I like it.
So I think we're just missing Elahe. We're just missing Elahe. Ela. Okay. So I heard that the assignment was difficult. So let's. I'm assuming. Okay. I have a few questions, and I will do some of the problems with you live on my screen. But what is it? Is the formalism unclear? Is the Python module not clear? Is Python not clear? Where are the issues, the problems? No, I can't say you don't know where the problems are because that's partially the question. So when you try to get started, where do you get stuck? Aha. Valérie? Okay. Shadi? Nice.
Question number 2, I got stuck. I had some problem. I didn't get the question explanation completely.
Okay.
Yeah.
But,
and aside from Python, since I don't know Python very well.
And the code that I had given as example was good enough, sufficient, insufficient, complicated?
Well, in my case, it was good, but still I don't know how every function of retracing worked. So I really needed to open raise.py, look at how you did it, and
okay. So let's take a look at the first question. The first question was the confocal pinhole, because I don't think I'm trying to. I will quickly take a look at some of the assignments that I got, but yeah, okay. Well, I don't think I got the answer that I expected from anyone, but I'm not sure. That's what I was trying to look, but I don't want to insult anyone. So what was I trying to get? Let's go take a look. So what we're gonna do, okay? I'm not teaching right now. We're just chatting, okay? We're chatting. We're talking. We're talking. So I will open my computer. Done. And you're gonna take. I'll do the problem. I'll do problem 1 with you live. Okay. So all right. So we're gonna look at my screen. I hope I don't have anything to hide. Yeah. Code. I have a lot of code to hide. Okay, and I'll quit Fortnite and everything. Okay. Okay. All right, we're getting there. Okay. This. All right. Okay. So let's go. I'll go to the assignment right here. Okay, confocal detection. So I will do the problem with you. Okay. So, and the question, you'll see that the questions are much easier than are not difficult. Okay. So the first one was, what should the size of the okay, I'll stop saying, I'll stop speaking in the past. I'll speak in the present as I am doing the assignment now. Okay, so what should the size of the confocal pinhole be to match the size of the focal spot? Okay. Okay, well, let's look at the microscope. Okay, right, whoops. Yeah, right here. Okay, good. Ah, not good. Good. Okay, so like this. So we have the microscope. Everyone sees the everyone sees my screen. So the laser is coming here. This is not relevant because that's illumination, and I'm going to talk about detection, but I will still speak. So light is coming this way here. So the beam is not moving here. Okay. Oh, here it starts moving. Good. Zoop. And now there's a relay. There's a relay from here to here. So a relay is a telescope. It's a 4F system. So this point here is imaged here. That I know, okay? Because it's a relay, right? Okay, and this is scanning in the other direction. Oh, okay. This is scanning, and I'm hoping to get to my sample. So scanning is a Fourier conjugate of the object plane because it's an angle. And in the object plane, I scan position. Okay. All right. So okay. So scanning point here, relay here, and relay to the back of the objective. And then the objective. Okay. Aha. Here's my focal spot. My focal spot is here. So here I have something that is, for the sake of the discussion, let's say 1/4 of a micron. So lambda by 2 when I excite in the green at approximately 500 microns, approximately. Okay, so here I know the spot because it's an objective. We know, you know, we know that when we focus properly in an objective that has a numerical aperture of approximately 1, we get a wavelength, we get a spot that is lambda 0.6 times lambda divided by NA, right? We know that. So with 500 microns, that gives us 200 not 500 microns, 500 nanometers. That gives us 250 nanometers. So that part we know. We know what the size of the focal spot. So everyone should see that we know the focal spot from the objective. Okay. So now this point here, okay, now I want it, the light is emitted from the focal spot and it goes all the way back to the pinhole. Okay. Let's see. So here, so I have the microscope objective and I have this here, and this is a relay, right? This is a relay, objective, first lens, I have a relay, and the conjugate plane is here. Okay? The focal spot here, 4F system, this is the image, okay? Then this is also a relay, and it's imaged here. So now, if I were to oversimplify absolutely everything, okay? From here to here, I have an image of the focal spot. From here to here, I have another image of the focal spot. So I can already, with just a few multiplications, I know that here, I have an image of the focal spot. And what is the size of that image? Let's see, what is the 4F system from here to here? This is a 5mm lens. This is a 10mm lens. 100 divided by 5 is 20. So the spot here is 20 times larger. And here I have another relay, 175. Now it reduces the magnification by 3/4. 3/4 of 20 is 15. So here I know right away, without even doing any fancy calculation, I have an image of the focal spot, and it's 15 times the size of the focal spot. Do most people see that?
Yeah.
Yeah?
Mhm.
Okay. So now I've taken this fairly complicated system and I'm transforming now the problem, because if the focal spot here is 1/4 of a micron, and this here is 15 times that, I will open my superb calculator. 0.25 times 15. Good. So here I have a focal spot that's 3.75, an image that is 3.75 microns, right?
Yeah.
Okay. So now what happens? The light will go here, here, hit this, then the pinhole, then the lens into the pinhole and into the detector. Okay. So let's just let's just simplify what is going on here. I have an image at the focal plane, at the focal spot of a 40mm diameter lens, 40mm focal length lens. And I'm sending this at infinity. And then this image at infinity hits this lens and is focused, and 50 is almost 40. So let's assume that just for now, let's just say it's the same. Okay, let's just say it's the same. So I have, this makes an image at infinity. So then I have an object at infinity that is going through this lens. So how big will the image be at the pinhole?
3 point.
Say that again.
Well, 3 point. I don't
Yeah, it
remember.
will be the same.
It's going to be the same, and with the real numbers, it's just going to be it's going to be 50 divided by 40 times bigger. So with the real numbers, 50 divided by 40 times 3.75 is 4.68. So even without the matrices, with simple intuition, the pinhole here, if the pinhole is, let's just round it up to 5 microns, 5 microns here is imaged onto the pinhole as 0.25 microns. So if I'm looking at the question again, what should the size of the confocal pinhole be to match the size of the focal spot? The first part of the answer to that is, well, does the question make any sense? Is the pinhole a conjugate plane of the focal spot? That's really the first answer. Are we really imaging the focal spot here? And just because I'm quite sure no one noticed it the first time around, do you remember when I came here, when we started, I said, the beam is coming in, this is a relay to here, this is a relay to here. You remember I said that?
Mm-hmm.
So this is a Fourier Fourier conjugate of the objective, and it's imaged here. This is imaged here. On the way back, do you notice that I'm, instead of, where's my pen? I need a pen. Where's my pen? How do I do that? How do I write on that thing? Annotate. There you go. Okay. Annotate. Oh, there you go. Okay, everybody can see that for the laser going in like this, I have this relay and this relay that brings us here, right? So now I'm clearing everything. On the way back, this is the first relay, and this is the other relay. Do you see that they're not? It's not the same match on the way. For the laser, yeah, for the laser, we say, oh yeah, the scanning point is relayed here, and then it's relayed here. Okay, so these two are the relay, and these two are the other relay. Whereas on the way back, we are looking at 4F systems for this object. And the first lens is this one, the second is this. So this is a conjugate. And then here to here, that's another conjugate. Okay, so that's how I know that this point here, the pinhole, not the pinhole, the focal spot is imaged here. And from here, it is imaged here. And then I can start doing a little bit of, there you go. Then from here, I used a little bit of, it's not magic, but I argued intuitively that this point here, we know right there, you know, that first part, okay, we have imaged everything here. And then it's okay, what happens for that last part? So now let's try to code it. Okay, let's try to code that. Let's just see if we can do that. Okay, so let's see. I need to delete. Am I saying things that are making sense? Yeah. Okay. Okay. Then perform the calculation using ray matrices. You should check your answer with Python and ray tracing if you can. Well, let me try that. I will start with an empty computer, an empty file. All right, I will code that right before your eyes. How do we do that? Okay, we do from ray tracing, import everything. That's the first thing we do. So that, let's call that devoir 3. So devoir, by the way, Shadi, is assignment in French. Okay.
Mm-hmm.
Okay. So we start. What I'm gonna try to do is I really hope to get from the pinhole all the way, from the focal spot all the way to the pinhole. Did you see how I keep confusing both all the time? There's actually a reason why, to me, they're almost the same. One is the image of the other. So whatever happens at the pinhole, well, the same thing will happen, but smaller at the focal spot. You know, they're conjugate, they're image plane, they're object image. So that's why, to me, it's really the same thing. But anyway, let's go back. All right. So what do? We start by creating an imaging path. Why do we create an imaging path? We are interested in tons of things in ray tracing, but the first thing we'd like to do is get some object, some image. Okay, so we start we're going to start from the focal volume and go all the way to the pinhole. So what do I add to my, I'm at the focal plane. So then I'll move a distance, To simplify, I will do focal length of objective is 5 millimeters. Focal length of the first lens, let's call that the tube lens. Yeah, no, I'll call it 4.
1.
Just number them.
Yeah, I'll number them. Yeah, exactly. 4, it's 10. Lens 3 is also, 100. Lens 2 is 75, 70. And lens 1
No, 75.
Is it really 75?
I think it's 75.
Is it?
Yeah.
Oh yeah, and the other one is 40. Okay. Yeah, okay. Not that I have designed that microscope. Okay, so we're here, space. So we're gonna move a distance objective.
Well, you miss a lens, right?
Yeah.
Which one?
The
Just before the
50
pinhole.
lens before the pinhole.
Oh yeah. And I'll call it FPH for pinhole. Okay. So we start at focal spot of objective. Okay. So we move a distance. Okay, I'll make it. There you go. We move a distance. Focal length of objective, and then we have a lens that is approximately the focal, not approximately, precisely the lens with a focal distance of the objective. So far, so good?
Yeah.
Okay, so here, where am I at this point? Where am I? Space, lens, space. So F through the lens, then F. Where am I?
At the focal
Back
spot
plane.
of, yeah, okay.
On the other
F4.
side, which is the back aperture of objective. I'm precisely right here. Okay, we continue. Okay, then I would like to move. Okay, okay, then I'm gonna move a distance F4, and I'm gonna go through this with a lens of a focal length F4 and this. Okay, so for now, let's just stop here. Okay, what do I have here? Okay, I have this, and I did from here to here, right? Okay, so let's just see if what can we do with this. So I have the path. What can I request from that path? Path is imaging. Okay, print is this imaging? And then we write like this. This is the way to do it. Tick, tick. Okay, is this imaging? If it's imaging, it's going to say yes. If it's not imaging, it's going to say no. Let's try that. I open my terminal. I run this thing. Where did I save it? On my desktop. Okay, I'm going to my desktop. It's a little small, so let me make this bigger. Okay, Python, BPH. Is this imaging? True, okay. And let's try path.display to see what this whole thing looks like. Okay, oh, it looks funny, okay. Let's not worry too much about the details here. Okay, can I zoom out? How can I zoom out? Can I zoom out?
The home button.
You can zoom out.
Yeah, but I don't remember how. Is it?
I think it's the bigger you can zoom in. Yeah, this is the.
Yeah, this is zoom in, but I want to zoom out. How do I do?
I don't think you can.
Yeah, I'm not sure it's possible.
The home button is the.
Yeah. Okay.
Zoom out.
Well, it doesn't matter. Okay. Qu'est-ce qu'il y a, Rémi? Ok. Une idée, ok? Donne-moi 20 minutes puis je vais parler avec toi. Qu'est-ce qu'il y a?
My reaction exactly.
Yeah, but did you figure out what the code is for to get screen time on your iPhone? Well, they haven't. Okay. All right. All right. So we start from here. There's a lens. There's another lens here. So this is actually the worst. This is the worst figure because it assumes an object of 1 millimeter. So I will kill this. And I will make this simpler by doing path object height is, let's take something that's very small. Like what? Like 0.00025, right? That's probably too small. So let's take.
Yes, it is.
Yeah, I'll take 10 microns just so we can see it on the screen. Okay, I'll make it just a little bit bigger so we can still see it. So 100 microns. All right, okay. So what do we have here? Okay, we knew that it was going to be imaging. And so we have our object and we get an image here. And what is the magnification? Well, let's try that. All right, magnification up. Print, is this imaging? Yes. Print magnification. Magnification. Magnification is, let's run that again. We see again the figure, which we don't care so much about, but whoops, magnification is bound matrix magnification of object. What's the exact call then? Well, let me see. Let's go take a look at. Okay, we're stuck in Python. What do? We open Python. We do import ray tracing. That's what we do. Then what do? We type help ray tracing dot matrix like this to get information. Did you know that? And we type imaging path. Imaging path has various functions, and one of them should be image size. Image size, okay, I don't have a magnification function. I only have an image size function. That needs to change. But image size, is, go back here, schluck, kill this, run the program, stop showing this, I'm an idiot. Excuse me, image. No, I think it's like this. Why am I an idiot with my own code? Help me here. What am I doing wrong? Image size. I was just using it fine. Python, import, ray tracing, imaging path. We have the imaging path, and I want image size. The image size is the image size. So image size is fine. What am I doing wrong? Okay, let's go back. I think I know. Magnification. I think this is going to be fine. Yeah, there you go. Okay, I got it. So I figured it out. Magnification returns actually the transverse magnification and the angular magnification, something I will need to document better. So the very first element in this is the transverse magnification. So we do that again. I will stop printing it to the screen because this is not helping. Like this. Oops. Run the code. What do we get? Woo! Is this imaging? Yes. And magnification is -20 because it inverts the image, but we knew that. Okay. So far, so good. All right. So now I have a few things in the code that are making this simpler. Do you see that we keep doing space, lens, space? We always do from focal spot, lens, focal spot, we keep going from one to the other. There's something called a system 4F. So I can do this, pat happened. Okay, we're here now, and okay, we've propagated all the way here. And then what do we have? We have 10 millimeters with 75 millimeters. So I can do system 4F. F1 is 100 millimeters. F2 is 75 millimeters. So now I'm here. You see that? This makes the code thinner because I've replaced all of this with a single call because it creates a 4F system in one shot. Okay, so now let's see. What am I going to get when I run the code? I've added an additional relay, and the relay will reduce by 3/4. So I'm going to get, is this imaging? It's going to write true, and the magnification will be +15. Woohoo! Okay, so far so good. Everyone sees this?
Yeah.
Are machines. Okay, we keep going. This is an important problem set. It's due tomorrow. So let me rush through. So I'm here. So what am I going to do now? I'm going to propagate a distance 40 millimeters. Okay. And then through my lens. Okay. My lens F1. Okay. Then I don't know this distance. Nobody asked me. But you don't need to know.
Does it matter?
Nope, it doesn't. It really doesn't. Okay. So I will tell you that it's approximately 50 centimeters, so 500 millimeters, but you'll see we can change it and it won't matter. Okay. So now okay, here, just before lens, just before, let's say, polygonal lens. Okay. Okay, so now, okay, space. We're going to propagate approximately 50 centimeters. Then we have another lens. That lens is the lens of the pinhole. And then obviously we're going to move all the way to the focal spot, F pinhole. All right. So I have the whole system from here to here, and it represents the system from here to here. Okay. Is this imaging? Let's see. Yes, it is, and we're still imaging what's at the entrance, all the way at the end, all the way to the end of the system. The magnification is approximately 20. Good. Did I make a oh, I think I made a mistake when I did the calculation earlier, because I ended up with a magnification that was, what was the magnification that I used? Let's see. 0.25 times 18.75. Did I make a mistake? No, it's the same number. Okay. All right. Okay, so the question here was, what should the size of the confocal pinhole be? Blah, blah, blah. Well, it should be in this system 18.75 times larger than the focal spot diameter. So the light that's focused at the focal spot will go through the pinhole, and anything that is around will not go through the pinhole. Okay? All right. So, as is described, so we're done with the first part here. Question 1 is done. Anyone got that part in the assignment? Yes or no?
Yeah, I got it.
Okay, good. Julien,
Yeah.
Shadi?
Yes.
Yeah, okay, Julien. If you're not sure, that everyone can say, I don't know, that's fine. I think the most essential part of research is to say, I don't know when you don't know. Okay, so we did not discuss this, but we can obtain the intensity of a point source at the image as a function of the source intensity by sending a large number of rays in all directions and computing how many make it to the image. Okay, that's interesting. What does that mean? Let me go back to the image. Okay, so now we have, I can take a ray on axis. I have points or rays that are coming from a tiny disk that is 0.25 microns, and I can send rays from that point and see if they're going to go through the pinhole. If I take any ray from the focal spot here and I send them in this matrix, will they go through the pinhole or not? If the pinhole is 18.75 times larger than the focal spot, will they go through? It will perfectly go through. They have to. They have to. Because anything here, the focal volume is perfectly imaged on top of my pinhole. So if I have a ray that's perfectly on my focal spot, well, then add the pinhole, it's going to be on the pinhole. So it's going to go through, for sure. Let's try that. Okay, let's try that. We have functions in this. Okay, so we have the first part. So now we have functions. Okay, random uniform rays, y max. Let's put that straight on axis. Okay, this is the code that I think I gave you, right? Okay, and rays. Okay, I'll use it directly. It's going to be so much easier. Okay. Okay, all right. Okay. Cut and paste. Total plagiarism. Okay, so if I take 100,000 rays and they're currently directly on axis, and I take each ray and I trace through the system. So I take the ray and I go, where is it going to get? Okay. And if it's blocked, then I don't count it. And if it's not, if it's not blocked, I count it. And if it's blocked, I don't count it. So far, so good?
Yes. Mm-hmm.
Okay. So I forgot one thing here. I'm not sure if I had it in, yeah, okay. That may be the thing that kind of, okay. So right now, what I'm going to do is that I'm going to put an aperture at the tip here. Okay. So there's an element called an aperture. So the pinhole is really an aperture with a certain diameter. So I'm at the end, just at the pinhole, I will put a pinhole. Does that make sense?
Yep.
Yes, no, maybe. Okay, I'll take and everything is in millimeters. So 100 microns, 10 microns, 1 micron. I currently have a pinhole that's 1 micron at my pinhole. Okay, so I will send 100,000 rays. I'll just take less so that it's faster for the sake of the discussion. And I'm sending all the rays through. Let's see what happens. Okay, so I go here, I clear, so you can see Python assignment. Okay, it sent, okay, I can use 100,000 then. That's fast enough. Okay, again. Okay, it's sending 100,000 rays. Okay, then it tells me it sent 100,000 rays and all of the rays went through. None of the rays were blocked. Are we surprised? What did I send through? I sent a bunch of rays that were perfectly on axis. Yes, no, maybe?
I might have a question for that one.
So now if I say that the rays are going to be up to 5 microns. Oh, just a second. Qu'est-ce qu'il y a, Coco? Tu veux jouer un autre jeu? Oui, oui, donne-moi-le, puis je vais te donner du temps. Je vais te donner du temps. Regarde, il faut donner du temps. Le code du temps d'écran. 1, 2, 3, 4. Oh non, je l'étudie tout haut. C'était pas ça. Tiens. Okay. So it's not a surprise that everything went through because I took a bunch of rays straight from the focal spot, perfectly centered. So of course they all got imaged to the center of the pinhole. So of course they all went through. Okay, so now what I'm gonna do is that I'm gonna say, I'm gonna take rays that go from 5 microns to -5 microns, like this. So from the focal spot, I'm taking rays that are in a disk of 10 microns of diameter, so 5 microns of radius. I remind you that my pinhole is 1 micron in diameter. So what do you think the efficiency will be at the tip at this point?
Small.
Let's run it.
It will be reduced.
It's going to be 1%.
I might have a question for that part.
0.5%. Why half?
Je m'entends pas.
Interesting. Should have been 1%. I really expected 1%. Okay, I'll have to double check this calculation, but let's assume it's fine for now. Okay, what happened? I took stuff that was spread over 10 microns here. So here, oh, I'm an idiot. There's a
maybe it's related to the diameter of pinhole.
10 microns here gets magnified by how much here?
18.
Let's go back to the code. By a factor of 20. So my 10 micron spot size became a 200 micron diameter at the pinhole, and 200 with a tiny pinhole of 1 micron, I'm getting 5%. Makes sense? Yes, no? Okay. What did we really want to do? What's the question? Okay. I will give you the video of this discussion, by the way, and I'll give you all of my code. Okay. We did not discuss this in class, but we can obtain the intensity of a point source, blah, blah, by sending a large number of rays in a direction, computing how many make it to the image. That's what I just did. You will find an example for a system below with an isotropic. That's what I just did. Using ray tracing for your confocal microscope, plot the intensity going through the pinhole as a function of the source position Z around the focal plane. For instance, for a pinhole of the size found in 1 and a pinhole 3 times smaller and 3 times bigger, parenthesis missing. Okay, so what do we want? What does he want, this annoying professor? He wants that just before, okay, just before, so I will position myself, okay? There's my focal spot, my focal volume. I want to be just before, and then move closer, 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 then to the focal spot, and then to beyond, 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 beyond. And I want to see how much light goes through if I'm perfectly at the focal spot. We know when we're perfectly at the focal spot and the pinhole size is right, we get 100% of the light. But if I'm before, not all the light is going to go through. We know that's the idea of the confocal microscope, that the pinhole will block the light. So that's what we're going to do. So what am I going to do here? I have this, I have my path, and I have all of this crap here that is a little bit, that makes it a little complicated. And I will now say for Z in range, like this, for distance D, for distance D, and I'll do Z will be 5 minus D times. Okay, so what am I doing here as a Python, for Python? I'm saying D will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to use Z. It's going to be 5 minus this. So it's going to go from approximately -5 to +5 times 1 millimeter, 1 minus 3. So it's going to be 0.005 minus 0.005 to plus 0.004. Okay, because the last one, okay, I'll just use 11. To minus 5 microns to plus 5 microns. Do we see that? Okay, so I have everything here. I still display this stuff, and then I'll calculate all of the rays, and I'll calculate the transmission efficiency for all the distances. Okay, transmission efficiency at Z. Z. All right. So I will not write the other things just to make this simpler, and I will not write the magnification just to make the code simpler. Okay. All right. Let's leave the output simpler. Let's see. What do we get? Calculating the first one. So I got 0.003. No, 0.00. Est-ce que ça paraît que je suis occupé, je suis en train de parler en anglais du monde?
Peux-tu mettre ce sujet dans le lavage?
Tu peux mettre ce que tu veux dans le lavage. OK. So what do we see? 5, we get 0.3% transmission, 0.4, 0.5, 0.52, 0.49, 0.52, 0.598. Is this working? I think it is mostly working. Okay. I forgot one thing. Okay, I have my pinhole that's very small, and here I assume that my spot was. I will take everything directly on axis just to make it simpler. Okay, I'm starting again. What size do we want our pinhole again? We want our pinhole to be 4.68 microns, right? So I'll just say 5 microns for now. Okay.
Well, this is the radius.
This, and I will not display the progress.
Can anyone hear me?
So
I guess Daniel doesn't hear us.
0, 1, schlock. Okay, like this.
Daniel.
Okay, doing it again.
Daniel?
Can you hear us?
Daniel.
Okay.
So it's giving me.
That's nice.
Who's making fun of me?
Can you hear us?
Hi.
Daniel?
Non, me parlez-vous?
Yeah.
Yeah.
Ah, là je vous entends.
That's why we were.
We've been asking questions for like.
Désolé. Je sais pas pourquoi mon son est enlevé. Calé. Bon, on recommence. So when were the questions?
You put the radius for the pinhole instead of the diameter for the diameter.
Okay. So
0.005 was the radius, but I actually
okay.
Might not matter.
Okay. Okay, fine. Okay, so I'm really sorry about that. So that this should be 0.05, so that should be half of that, right? No.
No. Times 2. Like,
Times 2. Okay,
that
so
was the radius.
10.
Yeah.
Good.
And I had a question for your function random uniform rays.
Yeah.
I saw in your code that it's sending rays randomly from pi over 2 to minus pi over 2.
Uh-huh.
Something I don't understand.
Okay.
Is if I set 100,000 rays,
Uh-huh.
how can all of them pass through the optical system? I mean, if a ray go with an angle of pi over 2, it won't go in the system.
No. The maximum is not pi over 2. It shouldn't be.
Perhaps I saw it wrong.
Mm-hmm. Oh, no. Yes, it is pi over 2. But in what I have here, I have infinite lenses everywhere. This is what I wrote. I don't have any, there's nothing to block the light except the aperture.
Well, even if you have finite lenses, it still has a 100% transmission for me.
Yeah, same for me.
Finite lenses?
Yeah.
Okay, I'm gonna have to look at it, but I've tested that quite a bit. But,
It's as if the rays magically went into the first lens.
okay, I'll take a look at it. How about that? So okay.
Okay, but it's fine. I mean, we don't. It doesn't matter for.
Okay, but let's. I'll write the diameter here.
I don't know.
Centimeter. Hein? Je suis occupé, Rémi. Là, ils m'entendent à cette heure. C'est plus bête. Comment? Pas tout de suite, on va souper. Mais là, comment ça, OK. Regarde, demande-moi-en, je vais t'en donner du temps. Donner du temps. C'est ça, c'est la vie des nouveaux parents. Donner du temps sur le téléphone. OK. Là, maintenant, qu'est-ce qui arrive? Là, il ne faudra pas que ça donne 1. Ouais, ça ne va pas donner 1.
Well, you doubled the pinhole size, and it's kind of twice the efficiency.
No. I had the efficiency here was 1 when I was perfectly at the focal spot, as I said, because nothing was blocking the light.
Okay.
And now it's 0.63. Okay, I will give you this code to everyone. Okay, I'll write that the diameter of the first lens is humongous. Okay, and you'll see that the transmission efficiency when I'm perfectly at the at 0, when I'm at the focal spot, you'll see the transmission efficiency is going to be should be essentially 0, essentially 1. Oui, ça sera pas long. Je vais répondre à ta demande de temps, mon coco. Et là, à 0, ça devrait donner 1. Et que je vis dangereusement pareil. All right, so the efficiency is 1 when there are no other apertures. So you made a mistake when you coded. Okay.
Yeah, but how can all the rays go into the system if it goes randomly from pi/2 to minus pi/2?
Because there are no apertures. There's nothing to block the light.
But if a ray goes to pi/2, I mean
but it's never pi/2. It's pi/2 minus a tiny little epsilon, very small angle. So it is moving a tiny little bit forward. Okay. And because the lens is infinitely large, it will eventually make it through. Okay, just a sec. I will give time to Rémi. Comment ça, toi, si tu veux encore du temps? Rémi, gaspille ton temps. C'est bon. Lui, je ne donne pas de temps. Fait que lui, il prend ton temps. OK. Là, vous voulez jouer à Roblox? Je vous donne 15 minutes. OK? Pas long. L'instant. Quand je disais c'est pas un cours, ça compte pas. Je ne suis pas en train de ne pas vous donner le cours parce que c'est pas un cours. On parle. Là, maintenant, il faut que je donne du temps à Luc. Sinon, c'est pas juste. C'est pas facile, la justice. OK? Bon. All right. OK. Where was I? I think I'm losing my train of thoughts here. Okay. All right. So what is important? You see that the efficiency is low. The efficiency is a few percent, and then when I reach the focal spot, it goes up and then down. Okay. Do you see that it obviously goes up very quickly? Okay, it goes from 2% to 1% very quickly. So now I'll change this. Okay, here. Okay, instead of saying that it's going to go from -5 to 5. Okay, what I'll do is that I will do this.
Sorry, could you please explain again why D +5? I didn't get it.
The D range is a function in Python that that returns 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The loop here D is going to be 0 the first time, then 1,
Okay.
then 2. So here I'm just quickly doing math in my head to get, I want values that are around 0. So that's why I'm doing D plus 5. So the first time it's going to be 0 plus, oh no, I'll do D minus 5. So it's going to be minus 5. Then times 0.5. So it's going to be 2.5. I'll do, yeah, okay. 2.5. Yeah, okay. Let's try that. Okay. Let's do it again. Pinhole. And as I said, I'll give you the code.
Oh, great. You're still there.
What? Am I still there?
Hi, Emil.
Hi. I was
Welcome.
getting my car at the garage. So,
You don't say. Okay, so so tuna, it's up and back down. Okay, so I will here, I'll just remove all of this text and then we can plot it very simply. Okay, so let me do this. Let's do it again. I use software called Datagraph for plotting. It's the best software ever produced by mankind for plots. So it's not free, but it's really good. Are people chatting among themselves and making fun of me? Okay, that's fine. Okay. Okay, what do we see? We're going from 2.5 microns before, 2.5 microns after. So let me plot this as soon as we're done. I need a haircut.
Me too.
Don't we all? You should see Remy. My father-in-law gave him a haircut. Even he knows the haircut sucks.
Good God.
He's embarrassed. Okay, so here, schlock, data, plot. Look at this wonderful curve.
This is the question 3.
Oh, is it?
Right?
Okay. So let me go back.
Or
Yeah, let me go back to the question. Using ray tracing for your confocal microscope, plot the intensity going through the pinhole as a function. No, that's...
But question 3, what is it then?
Well, question 3 is estimate the fractional intensity that is detected. I kind of by setting I wanted, what I'm telling you is at the focal spot, let's say I have 1 million GFP molecules perfectly at the focal spot, or one molecule that I keep exciting. How much light is it emitting? And in what direction? It's emitting in absolutely all directions, right?
Yeah.
So how many rays goes into the system?
Yeah, that...
I didn't get that.
Yeah, okay, maybe the question wasn't clear. The detected efficiency for 100 photons emitted from the focal volume, how many am I detecting? And you will see that if you use all the apertures, you'll see that actually the limiting factor in a well-designed microscope is always the objective, which makes total sense. The objective really wants to see as much light as possible, as much of a cone of light coming from the point. But if, that's the part that's hard. We want a big numerical aperture, large numerical aperture to see as much light as possible. If we're missing some light, well, that's because we didn't try enough. But if the objective is getting a very large cone with a numerical aperture of 1, then I would be pretty dumb after to use lenses that are blocking some of the light. So in a good microscope, this is always the limiting factor is always the front aperture. I'll give you, it's actually fairly simple to calculate, but I'll give you that right after that. Okay, but this plot, anybody got this plot for the assignment?
Yeah.
Anthony, anyone else?
No, I didn't understood well the question.
But do you guys see that this is how a confocal microscope works? Because if the light is emitted directly at the focal spot that is the conjugate of the pinhole, all of the light goes through. If you're just a little bit before, no, the light goes down. The efficiency of the collection efficiency is going down very, very quickly. Because you can see at 2 microns, it's already 10%. So if you're just a few microns away from the focal plane, the light you emit is not detected. Therefore, you're not seen. So this curve here is the confocal microscope. You guys see that? This curve tells us everything we need to do. And if we change the pinhole, so I have a pinhole right now that's just the right size. Okay, who has ever used a confocal microscope? Can you adjust the pinhole size on a confocal microscope? Okay, do you sometimes do that?
Mm-hmm.
And what happens?
You choose the optical section thickness.
Let's try that. So we can work, we're confined because of the coronavirus. So let's adjust our microscope. So I'll take a pinhole now that is 3 times the size. Let's start with 2. Let's start with 2. Let's do the calculation again. What do we think is going to happen? Now the pinhole is actually bigger than the focal spot. It's getting bigger and bigger. So let's see. Okay, we used to have this curve here. Yeah, I'll try to keep them both on the same graph. This was the first one. Okay. All right. Okay, I'll reduce the number of points. It's too long. It's getting on my nerves. Okay. You can already see. Do you see that there's more light coming from around the focal spot? You're going to see that it's not going to be as steep. Let's try that. I'll plot this as soon as I'm done. And you can see that on both sides, it's perfectly symmetric. I only need half of it, but it's not as good looking. So that's why I'm using both halves. Okay, here, schlock. Ta-dam, and then second curve. I love this program. This. Okay, so the second one is not as steep because the pinhole is bigger. So it actually makes, so then that means, you're not getting an optical section that's as good, but sometimes in the lab, you want that because that gives you more light from everywhere. And you're saying, yeah, well, it's just, maybe I'm going to see more. And then when you're done, you'll reduce the pinhole back to reduce it and get nice slices. Okay? All right. Is that useful?
Yeah.
Okay. Good. So, Okay, we essentially did 1 and 2 in an hour. So obtain an estimate. This I will, I would prefer to focus on this part here. Okay, and then I have to go make dinner for my kids. Okay, so any questions for the number 1? And Emile, I'll send you we have everything on video.
Right, thanks.
We have a proof that we're late. And then we'll just give you the video for you to watch by yourself at home while you cry.
I will. All of that.
Okay, you better. Okay, so I showed you, okay, we all know why we don't put a relay to a lens, to an illumination light, because then if we do that, we get an image of the filament. We don't want that.
Mm-hmm.
Okay, and we use this strategy called cooler illumination, and then we use an additional lens and we image the lens at the back of the objective instead of at the sample. There's one thing I forgot to say in the course, and it took me a while actually to get this in optics. You know, sometimes now I'm telling you, you know, oh, the 4F system, and now this thing is called color illumination, and then there's this other thing that you can do that reduces the focal length, and then this other thing you can do, and it always looks like people are pulling that out of a hat. But it's very important to appreciate that people have been doing optics for hundreds of years. And then at some point, an intelligent person figures out, wait a minute, if we do this, we get this. So this becomes a recipe. So the relay, for instance, the relay, the 4F system that I keep talking about, you know, we say, oh, come on, this is so useful. It's a relay, it gets this, it's much bigger, you know, it magnifies the thing and it moves it here. Hey, so it's a recipe. Color illumination is another recipe. And there are others, including one for question 3 that is hidden. But, you know, at some point in optics, in optical design books, what they do is that they will say, hey, look at this. If you take 3 lenses and position them like this, and the radius of curvature of this one is 55.3 times the one from this divided by the index of refraction, you get blah. And say, holy mother, what is this? Okay. At some point, people have figured out recipes, and they're known. When you buy an objective from Olympus, they follow recipes to end up with the objective that they end up with. Okay. All right. Illumination here. Okay. You have 2 constraints, or are people? I have an idea, because I think I'm going to run out of time here. Is question 2 more complicated than question 1? Do you want me to continue, or do you want me to send you a video of the solution of question 2?
Personally, I haven't tried it yet, so.
Okay, Valérie?
I think it went well for me.
Okay.
I think.
Is anything that I said in question 1 helping for question 2? Okay, I know what I'll do. Do I know what I'll do? Okay, I'll just say one thing about this Lagrange Okay, I'm a little bit stuck here.
Well, who had question for number 2? Just ask your questions.
Yeah, because I'm starting to have some issues. Coming back. Ce sera pas long, Coco. Est-ce qu'il y en a, anybody has questions for number 2?
Maybe you can explain for us tomorrow.
Yeah, okay. And I have a few things to do tonight, but I will try to give you at least an outline. Okay, I'll send you something tonight. Okay, no, for tomorrow morning. Let's put it this way. I'll send you something for tomorrow morning. And let's just quickly, super quickly take a look at question 3. Okay, take a picture with your cell phone. And if you do that, 1, 2, 3, 4. Encore. Non, c'est pas ça le code. Essayé, hein?
Je vais essayer. Je vais essayer.
Ah ben ouais, c'est ça, je l'ai pas essayé. So, take a picture with your cell phone. What's the size, the focal length, and sensor size in your phone? What's the strategy here? There are 2 things that I wanted you to do here. Okay, I wanted you first to try to figure out how to get the sensor size from the field of view. That was really my question. But then you're kind of stuck because you need the focal length and the sensors. You can only get the ratio, okay? But if you look it up, you will find, okay. Let me, how do we get the, annotate here. Yeah, okay. So if you have the lens of the phone and you have the camera size, the sensor size, and you have a certain focal length, of distance, F, okay, focal length F, it's actually fairly easy to get the field of view. So if you take your phone, you take a picture, or even I could, let's say I take this camera here, and I can see that there's at a distance of approximately, let's make that my arm, about 1 meter. The field of view is about 1 meter at about 1 meter. Okay, so I know that at 50 centimeters right here, see here, my finger, when the light goes from here and into the camera, it's gonna hit the size of the side of the sensor. So I have me here and I have my arm, so I was here. So if I go through the center of the lens here, I'll hit the side of the sensor, because that's what I just did here. See? Here. Okay, so if we know this angle, and then if we know the focal length, we know the sensor size. If we know the sensor size, we know the focal length. Okay, but the thing that you'll notice that's exciting is that the focal length of the camera is probably longer than the thickness of your phone. That's really what I wanted you to see.
Mm-hmm.
That's weird, but it's fun. Okay, so if you take a look, you can, if you, there is a website that I found fairly quickly. Type to get the sensor size. The best part is to get the sensor size of your phone. You can type your phone model and you say iPhone 6 sensor size, and then photography or camera lens, because a lot of people interested in these things are doing photography. So you'll find all of the details. Okay, and I just wanted you to do very simple optics to figure out the field of view and the camera size. But the second, and then we can talk about it the next time we see each other, but the focal length is essentially the thickness of your phone. You should be puzzled. And I'll stop here for this because it's too exciting. There are tons of things I can tell you about it. But so yeah, the focal length is essentially the thickness of your phone. So how is that even possible? And there are two things that are possible. Rémi, ça fait comme à peu près juste 8 fois que tu me dis papa, 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 puis je réponds pas. Puis tu sais, je parle en anglais, là. Ça sera pas long. OK? Ça sera pas long. OK. There are two things. One of them is, well, there are two things. You can make the lens appear smaller, and you can do some optical things inside the phone to make it thinner. I don't want to say anything about it yet. Just look at it. Think about how can you make, if you have a focal length of 5 millimeters, how can that work? Just look it up. Look it up. Find stuff. Okay? It's a quick question, but I find that it's a fun question. Okay, so I'm going to send you more information about number 2 tonight. As soon as I'm done with dinner with the kids, I'm going to work on that and send that to you. Maybe a video or maybe a text. A text may be faster for me. Okay. Is that helping? I'm thinking everyone has a chance to resubmit their assignments if they want to. I don't really care. I care that you learn. I don't care to receive assignments and put grades. I don't care about grades. I want you to understand. So if you want to resubmit something else, let's say let's make that before Sunday morning. I'll give you tonight, tomorrow, and even Saturday. What's a Saturday now? Every day is Wednesday. Anyway, okay, that's my slogan, the coronavirus slogan. Every day is Wednesday. Okay, so all right. I hope this was useful. I'm sending you the code. I'll send you all of the code I can send you so you can play with it and then you can answer stuff. Okay? And I may send information to you in a few waves. As soon as I'm done with code, I'll send it to you. And then if I write up some text, I'll just give it to you. And so that you can work right away instead of waiting until I'm done. Okay?
Mm-hmm. Yeah.
All right. Bye-bye.
Thank you.
Bye. Thank you.
Bye-bye.